July 15, 1945. The Jornada del Muerto Desert, New Mexico. The storm is violent. Lightning cracks across the high desert, illuminating a 100-foot steel tower standing alone in the darkness. At the top of that tower, in a corrugated metal shack, a 25-year-old chemist named Donald Hornig is sitting next to the most dangerous object on Earth. He is babysitting the gadget. It is a sphere of high explosives, wires, and aluminum, barely 5 feet across. But at its absolute center, encased in tamper metals, sits a core of a metal that did not exist in nature just 4 years prior. It is warm to the touch. The radioactive decay is already generating heat, like a living thing breathing inside its metal shell. Hornig holds a telephone receiver, reading a paperback novel by the light of a single bulb, waiting for the rain to stop so they can trigger the end of the world as they know it. If the test fails, 3 years of frantic effort and $2 billion have been wasted. If it succeeds, the heat of 1,000 suns will bleach these sands into glass. But the real miracle isn't the bomb itself. The miracle is the metal inside it. That core is made of plutonium-239, a man-made element. Just 3 years earlier, the total world supply of this substance was invisible to the naked eye. Microscopic specks smeared on a glass slide in a university lab. The United States military needed kilograms of it. They needed pure, refined weapons-grade metal, and they needed it before Nazi Germany could build their own. There were no factories to build it. There were no blueprints. The element was so new it didn't have a spot on the periodic table. This is the documented story of how the DuPont Corporation, a chemical company that wanted nothing to do with the project, took a theoretical physics problem and turned it into an industrial reality. It is the story of how they transformed 600 square miles of Washington desert into the most sophisticated factory in human history, and how they did it in less than 11 months. December 1942, Washington, D.C. caused the strategic situation facing the Allied powers was terrifying. While battles raged in Guadalcanal and Stalingrad, a silent war of physics was being fought in the shadows. The equation was simple, but the logistics were impossible. To build an atomic bomb, you need fissile material. You have 2 choices: uranium-235 or plutonium-239. Uranium-235 is natural, but it is incredibly rare. It makes up less than 0.7% of mined uranium ore. Separating it requires massive centrifuges and electromagnetic plants consuming the power of a major city. That path was slow, painfully slow. The second path was plutonium. It was a theoretical lifeline. Physicists calculated that plutonium-239 would be even more fissile than uranium. It would require a smaller critical mass. It would make for a more efficient weapon. But there was a problem, a catastrophic problem. Plutonium does not exist in nature. It is a byproduct of nuclear alchemy. To get it, you have to bombard common uranium-238 with neutrons inside a nuclear reactor, transmute the atoms, and then chemically separate the new element from the fiercely radioactive fuel rods. In late 1942, the United States possessed exactly 0 production reactors. They possessed 0 chemical separation plants. They possessed less than 500 micrograms of plutonium. To build a single bomb, the War Department calculated they would need approximately 2 kilograms. That is a scale-up factor of 1 billion. The gap between what America had and what America needed wasn't just a manufacturing shortfall, it was a physical abyss. Intelligence reports, though often fragmented, suggested that German scientists, the men who had discovered nuclear fission in 1938, were years ahead. If Hitler's engineers achieved a self-sustaining chain reaction first, London, Moscow, and Washington, D.C. could be erased from the map. The urgency paralyzed the military leadership. General Leslie Groves, the head of the Manhattan Project, realized that academic physicists could not solve this. He didn't need a laboratory experiment. He needed a factory. He needed an industrial partner capable of handling lethal radiation, high-pressure chemistry, and unknown physics simultaneously. He needed EI, DuPont de Nemours and Company. But DuPont didn't want the job. They remembered the Merchant of Death hearings after World War I, where they were vilified for making gunpowder. They wanted to stick to nylon and explosives. They had no nuclear physicists on staff. Groves didn't care. The vulnerability was absolute. Without industrial-scale plutonium, the war could drag on for years, costing millions more lives. The order was given. The impossible had to be built. Before the factories could rise, the science had to be proven. The intellectual spark for this industrial inferno came from an Italian navigator named Enrico Fermi. Fermi was a Nobel laureate who had fled fascist Italy. He was brilliant, pragmatic, and possessed an intuition for neutron physics that bordered on the supernatural. On December 2, 1942, in a squash court underneath the bleachers of Stagg Field at the University of Chicago, Fermi directed a team to slowly withdraw cadmium control rods from a massive pile of graphite blocks and uranium pellets. It was called Chicago Pile 1. The Geiger counters clicked, then chattered, then roared. For the first time in history, humans had initiated a self-sustaining nuclear chain reaction. The power output was half a watt, barely enough to light a flashlight bulb. But the principle was proven. Neutrons were splitting atoms, and those neutrons were turning some of the uranium into plutonium. General Groves pushed DuPont to take over immediately. The man DuPont placed in charge of the technical interface was Crawford Greenewalt. Greenewalt was not a soldier. He was a chemical engineer, a company man, polished and precise. He had been working on nylon production. Now, he was told to oversee the construction of nuclear reactors that would generate 250 million watts of heat, 500 million times the power of Fermi's little pile. Greenewalt sat in the gallery at Chicago, watching the scientists. He saw the genius, but he also saw the chaos. The physicists were improvising. They were changing designs daily. In the industrial world, you freeze the design, then you build. In the world of quantum physics, nothing was frozen. The clash of cultures was immediate. The scientists, led by Leo Szilard and Arthur Compton, viewed the DuPont engineers as glorified plumbers. They thought the conservative corporate safety standards were slowing them down. DuPont engineers looked at the scientists and saw reckless academics playing with fire. Greenewalt had to bridge this divide. He had to translate theoretical physics into concrete and steel. The location for this massive undertaking had to be isolated. It needed massive amounts of water for cooling and electricity. It needed to be far from any population center in case of a catastrophic explosion. They found it in the Pacific Northwest, a sagebrush steppe in eastern Washington state, the bend of the Columbia River. A place called Hanford. Residents of the small farming towns of White Bluffs and Hanford were given 30 days to evacuate. Their homes were condemned. The tractors arrived in March 1943. The quiet desert was about to become the most radioactive place in the Western Hemisphere. The technical challenge at Hanford wasn't just difficult, it was fractal. Every problem they solved revealed 3 more problems underneath. The process required 2 distinct, terrifying steps. First, the transmutation. This was the job of the reactor, specifically the B reactor. The design called for a massive block of graphite, 36 feet wide by 36 feet high and 28 feet deep. Drilled through this graphite block were 2 Zavoru-4 aluminum tubes. Inside these tubes, they would push slugs of uranium metal canned in aluminum. Cooling water from the Columbia River would rush through the annular space between the uranium and the tube walls. It had to flow at 75,000 gallons per minute. If the water stopped for even a second, the uranium would melt, the graphite would catch fire, and the resulting radioactive cloud would poison the entire Pacific Northwest. The physics worked like this. As the uranium fissioned, it released neutrons. The graphite slowed these neutrons down. Some neutrons split more uranium atoms, keeping the reaction going. But others were captured by the uranium-238, turning it into uranium-239, which decayed into neptunium-239, which finally decayed into the prize plutonium-239. That was the easy part. The hard part was getting the plutonium out. After the uranium slugs had cooked in the reactor for months, they were ejected out the back into a deep pool of water. They were glowing with lethal Cherenkov radiation. They contained plutonium. Yes, but only about 2 to 50 parts per million. The rest was uranium and terrifyingly radioactive fission products like iodine-131 and strontium-90. This led to the second step, chemical separation. DuPont had to build a chemical plant that could dissolve tons of uranium in boiling nitric acid and separate out a few grams of plutonium, all while the material was so radioactive that a human standing 10 feet away would receive a lethal dose in seconds. No pumps existed that could handle the acid and the radiation. No valves existed that wouldn't leak. DuPont engineers designed a process called bismuth phosphate precipitation. It relied on the fact that plutonium behaves like bismuth chemically. They would dissolve the fuel rods, add bismuth and phosphate, and the plutonium would precipitate out as a solid cake, leaving the uranium and fission products in the liquid. Then they would dissolve the cake and do it again and again, cycle after cycle, purifying the material. But the greatest challenge appeared when they first turned the B reactor on. September 27, 1944. The operators withdrew the control rods. The power climbed 10 megawatts, 20 megawatts. The chain reaction was stable. The champagne was uncorked. The physicists congratulated each other. Then, strangely, the power began to drop. To maintain the power level, operators had to pull the control rods out further and further until there were no rods left to pull. The reactor, for no apparent reason, wheezed and died. It shut itself down. Panic swept through Hanford. The billion-dollar machine was a paperweight. It was the physicist John Wheeler who solved the riddle. He realized the reactor was poisoning itself. The fission process was creating a byproduct called xenon-135. Xenon-135 is a voracious neutron absorber. It eats neutrons millions of times faster than graphite. As the reactor ran, the xenon built up, eating the neutrons needed to sustain the chain reaction. It was like an engine choking on its own exhaust. The reactor was dead because it didn't have enough spare reactivity to overcome the xenon poison. This is where DuPont's conservatism saved the free world. When the scientists originally designed the reactor, they calculated they needed 500 tubes of uranium. DuPont engineers, obsessed with safety margins and redundancy, had insisted on building the reactor with corners capable of holding 4 tubes. The scientists had mocked them for the waste of money. Now, facing a dead reactor, they realized that the extra 504 tubes in the corners could be loaded with uranium. This added fuel provided the extra neutron flux needed to burn through the xenon poison. DuPont's over-engineering saved the Manhattan Project. Solving the physics was one thing, building the machine was another. The scale of construction at Hanford defies modern comprehension. In early 1943, it was a desert. By mid-1944, it was the fourth largest city in Washington state. DuPont launched a nationwide recruitment drive. They needed bodies. They posted vague ads in newspapers across the country for essential war work, with good pay and housing provided. They couldn't say where. They couldn't say what. 51,000 workers flooded into the desert. They came from the Midwest, the Deep South, and the urban East. It was a rough, dusty, chaotic boomtown. They lived in thousands of trailers and barracks. The heat in summer hit 115 degrees. The dust storms, which they called termination winds, were so fierce they would strip the paint off cars and send hundreds of workers quitting on the spot. Construction crews laid 386 miles of road. They poured 780,000 cubic yards of concrete, enough to build a highway from Seattle to Portland. They built 29,000 housing units, and they built the canyons. The separation plants, named T plant and B plant, were the most ominous structures on the site. Each was 800 feet long, 65 feet wide, and 80 feet high. They were solid concrete monoliths with no windows. Inside, there was a canyon, where the chemical processing cells were buried under 20 feet of concrete cover blocks. Because the radiation was lethal, no human could ever enter the canyon once operations began. DuPont had to invent an entirely new way of manufacturing, remote maintenance. They installed massive overhead cranes equipped with periscopes. Operators sat behind thick lead glass in shielded cabs, manipulating the crane controls to lift the concrete lids, disconnect pipes, and move buckets of dissolving uranium. They had to design special connectors that could be snapped open and shut by an impact wrench hanging from a crane hook 60 feet in the air. They practiced for months. They built mock-ups. They timed the crane operators. A mistake meant a spill of highly radioactive acid that could never be cleaned up. The workforce was segregated and strictly controlled. Women played a crucial role, working as secretaries, lab technicians, and famously, the Calutron girls. At other sites, but at Hanford, they were essential in the administrative tracking of the colossal flow of materials. African American workers were recruited from the South, segregated into the poorest barracks, and given the dirtiest construction jobs, yet their labor was the foundation of the site. Secrecy was absolute. Posters everywhere warned, "ZP yo Uralipu." Workers who asked questions were fired. Most of the 51,000 people building Hanford had absolutely no idea what they were making. They knew they were building massive factories that had no smokestacks, no assembly lines, and no visible product leaving the gates. Rumors flew. Some thought they were making high-octane gas. Others thought it was a torture camp for Hitler. Some joked they were making electric toilet paper. Only the inner circle knew the truth. They were building the mechanism of the apocalypse. By the spring of 1945, the T-plant separation canyon was operational. The remote-controlled cranes hummed, lifting the dissolved fuel. The bismuth phosphate chemistry worked. Small, stainless steel flasks containing a slurry of plutonium nitrate began to leave Hanford in modified ambulances. They were driven south to Los Alamos, New Mexico. The scientists there, led by J. Robert Oppenheimer, were waiting. They had already realized that the gun-type bomb design, which smashed two pieces of uranium together, would not work with plutonium. The plutonium from Hanford was too hot. It reacted too fast. If they used a gun barrel, the bomb would fizzle, blowing itself apart before it could generate a full nuclear yield. They had to invent an entirely new type of weapon, the implosion bomb. They would take the Hanford plutonium, shape it into a sphere slightly larger than a tennis ball, and surround it with precision explosives. When detonated, the shockwave would crush the plutonium sphere inward, increasing its density and triggering the chain reaction. This was the gadget, tested at Trinity on July 16, 1945. When the flash blinded Donald Hornig and the other observers, it validated everything. The physics, the engineering, the chemistry. The Hanford plutonium worked. 3 weeks later, on the island of Tinian in the Pacific, a second plutonium core, also from Hanford, was loaded into a casing painted mustard yellow and black. This weapon was codenamed Fat Man. On August 9, a B-29 bomber named Boxcar carried it over the city of Nagasaki. The bomb missed its primary target due to cloud cover and detonated over the Urakami Valley. The explosion was equivalent to 20,000 tons of TNT. The devastation was absolute. The moral implications were horrifying, but the technical validation was undeniable. The mechanism worked exactly as designed. The Japanese emperor, already reeling from the uranium bomb dropped on Hiroshima 3 days earlier, and now facing a second city obliterated by a different type of weapon, faced the reality that the Americans could now manufacture destruction on an industrial scale. The imperial surrender came days later. The war that had consumed 60 million lives was over. The atomic age had begun. The end of World War II did not stop the machines at Hanford. It merely accelerated them. With the onset of the Cold War, the demand for plutonium skyrocketed. The United States needed not kilograms but tons. DuPont, having fulfilled its wartime contract, withdrew, handing operations over to General Electric. The site expanded. They built more reactors, DF, HDRC, KWKE, and finally the massive N reactor. By the time the reactors shut down at the end of the Cold War, Hanford had produced 67 metric tons of plutonium. This material formed the core of the United States nuclear deterrent, the warheads for the Minuteman missiles, the Trident submarines, the gravity bombs. The American industrial juggernaut had proven it could master the atom, but the cost was high. The haste of 1944 left a dark legacy. To get the plutonium fast, they had sacrificed environmental safety. Millions of gallons of highly radioactive waste were pumped into underground storage tanks. single-shell steel tanks that were only designed to last 20 years. Today, Hanford is the most contaminated site in the Western Hemisphere. The cleanup effort costs the U.S. government over $25 billion a year and is expected to last until at least 2070. The total cost will exceed $110 billion. It is a slow-motion tragedy, a debt left by the desperate generation who felt they had no other choice. However, the technology pioneered at Hanford also birthed the civilian nuclear power industry. The knowledge gained in reactor shielding, control rod dynamics, and coolant systems paved the way for the 92 nuclear reactors that today provide nearly 20% of America's electricity, carbon-free power that is essential in the fight against climate change. The medical isotopes used in millions of cancer treatments and diagnostic scans every year are the direct descendants of the isotope separation techniques mastered in the concrete canyons of T plant. We return to the image of Donald Hornig in the tower, reading his book next to the bomb. He lived to be 92 years old, serving as a science advisor to 3 presidents. He spent his life wrestling with the genie he helped let out of the bottle. The story of Hanford is not a simple fable of heroism. It is a complex saga of brilliance, desperation, and consequence. It reveals a terrifying truth about American industrial capacity. When faced with an existential threat, the combined might of American science and industry can achieve the impossible. They compressed decades of research into months. They built a city in a desert. They transmuted the elements themselves. But it also teaches us that innovation under pressure carries a price. The waste buried beneath the Washington desert will remain radioactive for thousands of years, a permanent monument to the year 1944. Every time you turn on a light switch powered by nuclear energy or see a patient receive radiation therapy, you are touching the legacy of that frantic, secret year. You are using technology born from the fear that the enemy would get there first. It was the year engineers and physicists reached into the heart of matter, found a fire that could destroy the world, and decided to build a factory to mass produce it.